All right, so welcome to our first lecture for Physics 7D, Intro to Electromagnetism. A few things just about the math background that's expected of you for this class, or that you'll need to succeed in this class. This class is very, very heavily reliant on vectors and calculus. So we're going to be doing a lot of integrals, some derivatives, but mostly integrals, and a lot of vectors. The electric and magnetic field are both vector quantities, so essentially the whole course is based on vectors. So if you're not comfortable with vectors, definitely come to my office hours and we can go through it. We can make sure that we clarify anything that you're uncomfortable with. And as I go over problems, I'll make sure to take a little bit of extra time to go through the vector part a little bit more carefully, so that if you are uncomfortable with vectors, hopefully we can clarify any issues you have. Also, when we do integrals, never be afraid to come to my office hours if you're confused about how I did an integral or what a certain type of integral means. I know that this course isn't really the best with the math prerequisites that are required. There's a little bit of a mismatch. So if you're at all confused about anything I've done, please don't hesitate to come to my office hours. This class, the math is what trips people up the most, not the physics. So definitely make sure that any math problem you have, we address right away, because the physics is going to be hard enough. You don't need to compound that by having any kind of math error. Okay, so that being said, let's dive into it because we do have a lot to cover today. So we're going to be starting with electrostatics, and we're going to see the electric field of a point charge and just a little bit of background about electromagnetism in general. So the first thing I want to start with is just an overview of the four fundamental forces, since this whole class is devoted to studying one of them. So the four fundamental forces in our universe are gravity, the weak force, electromagnetism, and the strong force. So every interaction, everything in our universe can be described by these four forces, basically. So gravity is the one we have the most interactions with. Everybody's familiar with gravity. Gravity is only attractive, right? You never have masses that repel each other because of their gravitational field. Masses only ever attract each other due to gravity. And there's only a single type of charge, which is mass. You either have mass or you don't have mass. There's no negative mass, there's no different types of masses, it's just one type of charge, which is mass. Then next is the weak force. So the weak force is responsible for radioactive decays. So when you have a neutron that decays into a proton, an electron, and a neutrino, that's the symbol for neutrino, that's the weak force. So that's radioactive decays is the weak force, essentially. And then we have electromagnetism, which is what we'll be studying in this course, obviously. So electromagnetism can be both attractive and repulsive. And there are two types of charges. There's positive and negative. Or if something's not charged electrically, then it's neutral. Then we have the strong force. The strong force is attractive, and there are three types of charges. We call them colors. So they're red, green, and blue are the three types of charges in the strong force. And the strong force is what binds quarks together in the nucleus. So in the proton, we have protons and neutrons are made up of three quarks, and they're held together by the strong force. Okay, and then just a little bit more deeply about these four forces. So the strong force is obviously the strongest. The theory that describes it is called quantum chromodynamics. You'll see that abbreviated as QCD. So obviously we're not going to be getting into quantum anything. So that's just the theory that describes the strong force. And the force carrier for the strong force. Every force we have is mediated by some type of force carrier. There's something that transmits the force across distances. So for the strong force, those are called gluons. And they're called gluons because the strong force is so strong, they glue things together. They glue the proton and neutron together. So those are called gluons. And then for electromagnetism, the theory that describes that is typically called quantum electrodynamics, QED. So you'll see that Richard Feynman was a big, one of the pioneers of quantum electrodynamics. And then the force carriers for electromagnetism are photons. So I'm sure everyone has at least heard of photons. So those are light particles. So we'll talk more about photons in a minute. But photons are what carry the electromagnetic force over distances and mediate that force. Then the weak force We call that, the theory that describes that is electroweak theory. And the reason why it has that electro in there, it's not just like weak theory or quantum weak theory, it's electroweak theory, is because at very, very high temperatures, like a nanosecond after the Big Bang when the universe was extremely hot, electricity, magnetism, and the weak force were actually fused into one force. So these forces are actually the same force at high temperature, and then as the temperature cools to like today's temperature, it's not Big Bang hot, as the temperature cools, the forces split into two separate forces that we see today, the electromagnetic and the weak force. And it's theorized that all three of these forces meet at a very, very, very high temperature. And there's actually only one force that really governs everything, and it's just only at high temperatures is that sort of visible. But we're not getting into all that stuff. That's for another day. Okay, so the force carrier for the weak force is the W and Z bosons, the W plus minus and Z bosons. So there's three different force carrying particles that mediate the weak force. Again, we're not getting into the weak force, so that's really all we need to know about that. And then gravity. So gravity is described by general relativity, which was what Einstein came up with in the early 1900s. So gravity is described by general relativity, and the force carrier of that, we haven't discovered it yet, it's just theorized, is the graviton. So this is just theoretical. Who knows if we'll find it or not, but if we do find it, we'll call it the graviton. And then just about the strengths of these forces. So the strong force obviously is the strongest, and let's just set the strength of the strong force to 1. So we'll just say that that's like our sort of benchmark force strength, is the strong force at 1. And then compared to the strong force, electromagnetism is 100 times weaker than that. So compared to the strong force, the electromagnetic interactions are 10 to the negative 2 as strong. And then we have the weak force. So the weak force is not actually the weakest force, which might be a little bit confusing. The weak force, compared to the strength of the strong force, is 10 to the negative 6th. So it's significantly weaker than the strong force and significantly weaker than electromagnetism. There's 4 orders of magnitude difference between these. So it is pretty weak. But gravity is by far the weakest force, like suspiciously weak. So there's a lot of people that do research into why gravity is so weak, and we really have no idea why gravity is so much weaker than the other 3 forces that we know of. So compared to the strong force, gravity is 10 to the negative 38 times weaker, or as strong as the strong force. And even, compared to the weak force, that's still going to be a lot of orders of magnitude difference. So this is suspicious, and we don't know why gravity is so weak. And just to get a sort of understanding of just how weak gravity is, just how small 10 to the negative 38 is, I took 2 refrigerator magnets. So if I just have these 2 refrigerator magnets, which will attract according to electromagnetism, right? Magnets are the electromagnetic force. If I just hold one of these magnets here and then try to get it to attract, I can lift up this little magnet with just this little thing here, right? And it gets pulled up. So that means that this magnet, which is like maybe the size of a quarter, has a stronger effect on this than the entire Earth does, right? Because it's trying to sit in my hand with gravity holding it down. And so this little magnet is stronger than all of the Earth trying to pull this magnet down. That's how much stronger electromagnetism is than gravity. Okay, so now let's talk about electromagnetism specifically. So light is the most common example of an electromagnetic wave, or just anything electromagnetic in general. So light obviously comes from the sun, is all around us. So light is an electromagnetic wave. Obviously most of the things we use every day, computers, Wi-Fi, your car, everything is run by electromagnetism. Radio, it's all around us, right? And EM waves in a vacuum, so like in outer space, no air, no water, no nothing. EM waves in a vacuum will travel at 3 times 10 to the 8 meters per second. So this is an important number, so make sure that you sort of memorize that and always recognize 3 times 10 to the 8 meters per second as the speed of light. So all EM waves in a vacuum will travel at this speed, and this is sort of like the universal speed limit. Nothing can go faster than light. So if you're ever doing a problem in physics, it's always a good idea to have sanity checks on your work. If you ever find yourself calculating a velocity that's faster than this, you've done something wrong. Nothing can ever travel faster than 3 times 10 to the 8 meters per second. And one interesting thing about electromagnetic waves that sort of differentiates them from all other waves that we'll encounter is that they don't need a medium to propagate through. So electromagnetic waves can propagate through completely empty space. And when you think about the other waves that we know, none of them act like that. A water wave, like a wave at the ocean, obviously needs water to propagate through, right? If there's no water, there's no wave. The waves, like if you have a jump rope or any kind of rope and you shake it and there's a wave going down that, you obviously need a medium to create the wave, right? Without the medium, there's no wave. And you'll even notice when you study waves more in 7E, the velocity, all the features of the wave depend on the medium. So like the tension in the string, that will all contribute to how the wave propagates. But electromagnetism is different. As we'll see, the equations that govern electromagnetism make absolutely no mention to a medium because they don't need a medium to travel through. They can travel in completely empty space regardless. And so this is very odd and really tripped physicists up for like decades because they couldn't figure out where was this medium that electromagnetic waves were traveling through. There had to be a medium, and finally they realized there was no medium. And also gravitational waves can propagate through empty space, but we only just discovered those I think 5 years ago or something. So those are a little different. So anyway, so all other waves you're going to encounter in your physics courses are going to be mechanical waves that do need a medium to travel through. Okay, so then photons, as we mentioned before, are the force carriers of the electromagnetic force. So what we mean by a force carrier is that any electromagnetic interaction, so if we have you have two magnets like I just had, or if we have like a negative particle here and a positive particle here, they're going to want to attract to each other. And what they're really doing is they're emitting little photons towards each other. And these photons are interacting with the charges and creating a force. So that's what we say when we say photons are the force carriers, or a force is mediated by photons. So when I have these two little magnets here, they're exchanging photons, which might seem weird because there's like no light or anything. I can't see anything going on between them. But the force I feel between these two magnets is the exchange of photons. And then the other thing is that photons are massless and they travel at the speed of light. So only massless things can travel at the speed of light. If anything has mass, it by definition cannot travel at the speed of light. So only massless things like photons will be traveling that fast. Okay, so now let's move on to Maxwell's equations, which are the famous equations that govern all of electromagnetism. So Maxwell's equations were developed by a guy named Maxwell, James Clerk Maxwell. He developed them in the 1860s. And these were really like a revolutionary thing in physics. The development of Maxwell's equations really started ushering in, it was kind of the beginning of the whole revolution, the quantum revolution in physics, because they unified previously completely separate areas of physics. They unified light, they unified electricity, and they unified magnetism. Which when you think about it, it's kind of weird. Like when you have magnets, you don't really think like, well, this is also electricity. The same force that creates electricity is governing my magnets. So that's kind of counterintuitive. So it was really a revolutionary thing that he developed, was these equations that unified them all into one single force. Okay, and then we have Maxwell here and his wife and their dog. And I've never seen a dog with such a human-like face as that one. So I don't know if they like airbrushed it or something, but I think it's a interesting looking dog. So, okay, so that's Maxwell. And originally Maxwell's equations were written as 20 separate equations. So here I just included, obviously I don't expect you to know this. So this is just his original 20 equations, and this was because back in the 1860s, they didn't have vector calculus yet. They didn't have the formalism, the vector notation that we have today to write a vector as 3 components. They didn't have I hat, j hat, k hat. So he had to write a separate equation for each component. So he had 20 separate equations. And then when we developed vector notation, a guy named Oliver Heaviside developed vector notation. We were able then to condense these 20 equations into just 4, where it covers all the components. So we condensed it down to just 4 equations, which is much nicer. And if you are familiar with vector calculus, these equations are much more intuitive and very easy to understand compared to this. So we'll be focusing mostly, this is the differential form of Maxwell's equations because these are differential operators here. We'll be using the integral form since it's not a prerequisite for the class to know vector calculus to this extent. So we'll be using these, but I will also be going over these in addition because I do think that this form is much more intuitive and much more illuminating than the integral form. So we'll see both of them, but we'll be focusing mostly on the integral form here. Okay, so now we can go on to electrostatics. So electrostatics is kind of just what it sounds like. It's the study of stationary or static charges and the fields and forces they create. So when we're studying electrostatics, like this chapter, I think the next 4 chapters will all be electrostatics, you can safely assume that none of your charges are moving. So if we talk about like a charge, feeling a force due to another charge, you can just assume that the charges are like nailed down to the ground and they're not moving. So we just have our 2 charges and they're nailed down, they won't move. Another way to think of this is that our electric field won't depend on time. So we'll have an electric field that depends on our position, and it will not have a time component. Later in the class, when we're doing electrodynamics, we will have a time component of our electric field, but for now in electrostatics, we do not. Okay, and then what is electric charge? So electric charge is a fundamental property of elementary particles. So every elementary particle is either positively charged, negatively charged, or neutral if it's not charged at all. And we kind of take the positive and negative for granted, but I sort of want to point out that there's no real physical reason why an electron is negatively charged and a proton is positively charged. The point is that they have different charges. But there's nothing intrinsically negative about an electron charge and nothing intrinsically positive about a proton. We just sort of gave them negative and positive to make our math easy because it's easy to work with positive and negative. But I could have just as easily called it, like with the quarks and the strong force, I could have just as easily said a proton is blue charged and an electron is green charged, and the physics would be the same. So I just want to point that out, that there's, this is sort of just like a convention that we're using, that they're positive and negative. There's nothing really like physically justifying the use of positive and negative for these charges. Okay, then electric charge is measured in coulombs. And the SI unit of Coulomb, which is an ampere second, we obviously haven't done amps yet. That comes when we do current. But if you're curious, a Coulomb is an ampere second. And the other thing is that electric charge is conserved. So all of the electric charge that was like generated during the Big Bang or just after the Big Bang is all the charge we're ever going to have in the universe. We can't create charge, we can't destroy charge. So we're going to see in all of the problems we do, we can never create or destroy like an excess of charge. I can never create just a proton without also creating an electron to sort of balance that out. So electric charge is conserved. And this is a very, very fundamental property of the universe. And it was proven by a mathematician named Emmy Noether. She was alive like in the late 1800s, early 1900s. She proved the connection between symmetries and conservations of properties of nature. And the theorem that she created is called Noether's theorem. And if you take like classical mechanics or any higher level physics, upper division physics, Noether's theorem is everywhere. It's like one of the most fundamental theorems of physics. And she was so smart, even Einstein called her a genius. So she was a pretty big name in her time. And the theorem that tells us that electric charge is conserved is actually the same theorem that proves that momentum is conserved. So it might seem weird that momentum conservation and the fact that electric charge is conserved have anything to do with each other, but they actually are directly from the exact same theorem. The same theorem proves both. So then the other thing is that electric charge is quantized. So the fundamental unit of charge is the charge of a proton or an electron. We typically use that of an electron and denote it as E. I don't know why, that's just the way it happened. So the charge of an electron or proton is 1.602 times 10 to the negative 19 coulombs. It's obviously going to be positive for a proton. This quantity is negative for an electron, but the magnitude is the same. So this is a fundamental unit of charge. It's the smallest observable unit of charge. All other charges are integer multiples of this number. And you might say, like, well, why did they choose such an inconvenient number to be the fundamental unit of charge? Couldn't you choose like 1 Coulomb or something? That would have been nice, but unfortunately, most of these things were developed, the conventions were developed before we knew what an electron was. So that's why we have this sort of annoying unit of fundamental charge. And just to give you like an idea of how much a Coulomb actually is, like if you get a static shock from like rubbing your socks on the carpet or something, that's typically like micro coulombs of charge. So 10 to the negative 6 coulombs of charge are being exchanged there, whereas a lightning bolt is like 15 coulombs. So obviously like a coulomb of charge is a lot. Okay, and then we all know something already about the electromagnetic interactions. We know that like charges repel and opposite charges attract. I'm sure we've all heard the phrase opposites attract. So we all know at least one thing already. Okay, so now let's get on to the electric field of point charges. So point charges, like electrons or protons, are the fundamental building blocks of all other charge distributions, right? So the electric field of a point charge is like the most important one we'll do. So this is the electric field of a point charge. Now there's a lot of things, we'll go over each point of this right now. So the first thing is that I have a vector symbol over the electric field. So as I said before, the electric and magnetic fields are both vector fields, which we'll talk about more in a second. But keep that in mind, whenever you see a question that asks for the electric field, it's always a vector. So you need either components or your magnitude and direction. Then we have this combination of constants. So we have 1 over 4 pi epsilon naught. Epsilon naught, just take as a constant. It's given by this number, 8.85 times 10 to the negative 12. This is a Faraday per meter. We'll talk about Faradays in, I think, chapter 26 or 27. But for now, just take it as a constant, and we'll talk about this constant a little bit more when we do dielectrics also. Then we have the charge Q. So the electric field due to this charge Q is given by this. So this is just in coulombs. And then R down here is the distance from our point charge to whatever position we're measuring the electric field at. So if you're measuring the electric field 5 meters away from your charge, this is just going to be 5 squared. Be very careful, especially when we start doing spheres. A lot of people accidentally put in the radius of the charged sphere here. That's obviously incorrect, so just be very careful that you remember that this r squared is a distance, not a radius. And then the other thing is this vector here. So r hat, we're going to talk about that on the next slide, so I'll save that for a second. And then the electric field is measured in newtons per coulomb. Okay, so let's talk about this r hat a little bit more. So this r hat is the same r hat from spherical coordinates. If you've seen spherical coordinates already, it's that exact same r hat. If you haven't seen spherical coordinates yet, all it means is that, let's say we have some coordinate system, and we put a positive point charge in the center here. All that means is that our electric field is pointing radially outward from our charge. So in all directions, obviously I can only draw two dimensions here, but in all 3 dimensions, your electric field is pointing radially outward. That's what the r hat vector means. And again, if you haven't seen like r hat, theta hat, phi hat, definitely come to my office hours so we can just go through that a little bit, because that will be really important for this class. So r hat is just telling us that if we have a point charge at the origin, the electric field is pointing radially outward from that point charge. And then likewise, if we have a negative charge, so let's just redraw a negative charge. So if we have a negative charge at the origin, then the electric field is going to be pointing radially inward because we're going to have a negative Q, which means overall this will be pointing in the negative r hat direction. Oops. So we're going to have an electric field that's pointing radially inward like that. And those should be uniform, but yeah, pretend that's symmetrical. Okay. Now, if we have a point charge, let's say that's not situated perfectly at the origin, the r hat just means that it's the unit vector that points from our charge, so from our charge here, to whatever point we're measuring the electric field at. So if we want to find the electric field at this position over here, all that means is that r hat is just the vector in this direction. So this would be our r hat direction here. It's just from your charge to the point where you're measuring the electric field. That's all your r hat means for just some general point charge situated anywhere. Okay, so let's do an example now. So we have a positive point charge of 1 Coulomb at the origin. So let's draw that. So we've got 1 Coulomb at the origin, and this is positive. What is the electric field? So we want the magnitude and direction since it's a vector, at x equals 4 meters. So we're looking at this point over here. It's at 4 meters. This is 1 Coulomb. Okay, so our equation for the electric field, we said, was 1 over 4 pi epsilon naught q r squared r hat. So our constants are going to stay exactly the same, right? We can just rewrite 1 over 4 pi epsilon naught. Q, we said, is 1 Coulomb, so we can just plug in 1 here for Q. It's positive. And r squared is the distance from our charge to the point where we're measuring the electric field, which is 4 meters away. So we're just going to plug in 4, and that's squared. So we've got 4 squared. And then our r hat vector is the unit vector from our charge to the point where we're measuring the electric field. So in this case, this is obviously the x hat direction. So we have x hat here. Now we can just plug this into your calculator, just plug this number in, and we get for that, let's see. So this comes out to 5.6 times 10 to the 8. This is in the x hat direction, and the units are newtons per coulomb. So this is our electric field. So this electric field is kind of huge, 10 to the negative 8, because like I said, 1 Coulomb of charge is like very big. So typically our electric fields are going to be a lot smaller than this, like 10 to the negative 8 usually. Something like that, but I just chose this problem so the numbers are easy. Okay, then we want to know what if it was a negative charge? So if it was a negative charge, so let's just plug that in. So we'll say E negative. We'll start with the exact same equation, obviously, and then we're going to have still 1 over 4 pi epsilon naught. That doesn't change. And then Q, now we have, let's say, negative 1 Coulomb. So we're going to plug in negative 1 here. Our distance hasn't changed, right? We're still 4 meters away, we're measuring. So we've got still 4 squared. And then our r hat vector hasn't changed either, because from our charge to our point we're measuring is still in the x hat direction. So we've still got x hat there. And then again, obviously you can see, you'll plug in your numbers and you'll get negative 5.6 times 10 to the 8 x hat newtons per coulomb. So here the only difference is now your electric field points inward, right? So now our electric field overall at this 0.4 meters is going that way, right? It's pointing towards the charge because it's a negative charge now. And then one thing also I forgot to mention, so I'm writing here 1 over 4 pi epsilon naught. In your book, you might see, or in like a lot of places, we'll write 1 over 4 pi epsilon naught as k. That's fine on exams. I don't care if you use 1 over 4 pi epsilon naught or k. The only reason that I prefer the 1 over 4 pi epsilon naught way is because if you take any higher electromagnetism course, you don't use k anymore. You use 1 over 4 pi epsilon naught. So that's one reason, is just that this is like the convention if you go further in physics. And the other reason is that when we go into chapter 24, which is dielectrics, we're going to have other k's. So you'll end up with like a bunch of k's floating around, and it's not going to be obvious like which k is which. So that's why I prefer not to use k, because it just gets messy. So again, on exams, I don't care which one you use, just make sure it's clear when we get to chapter 24 what k is what. Okay. All right, so let's look at another example now. So now we have a positive point charge again of 3 coulombs. So let's draw that, and that's centered at the origin. So we've got 3 coulombs right here, and that's positive. And then we want to find the electric field at a point 4 meters to the right and 2 meters down. So we want to find the electric field down here, which is at position 4, -2. This is x and y. Okay, so we want to find the electric field here. So we can obviously see that we're going to have components 4 and 2, and we're trying to find the electric field there. So we've got a little triangle there. Okay, so what's the electric field there? So we're going to start with the equation for the electric field is 1 over 4 pi epsilon naught q r squared r hat. Okay, so again, we can just rewrite our constants. So we've got 1 over 4 pi epsilon naught. Q is 3 coulombs, so that's just +3. And now what is R? So R is the distance from our charge to the point where we're measuring the electric field. So we're going to have to use Pythagorean theorem here to figure out this distance R. So this is R down here. So we can just use R squared is going to be 4 squared plus 2 squared. So we can see that R is going to be 16 plus 4, which is square root 20. So we're just going to plug square root 20 as R, but it's R squared, so we just get 20. So we've got 3 over 20. And then what direction is R hat? So we have a unit vector in this direction pointing down here. So we're going to have to break this up into components or figure out the angle. So let's figure out the angle first, since that will be relatively easy. So here, we want to figure out what is this angle. Well, we can use inverse tangent for that, right? We can say tan inverse. Tan is opposite over adjacent, so opposite is 2, adjacent is 4. So we have tan of 2 over 4 is equal to 26.5 degrees. So this angle here is 26.5 degrees. So now you have 2 options for your answer. You can just calculate what this number is and say this is the magnitude. This is the direction below the x-axis, and that's totally fine. Or you can break it up into components and do it that way. So let's just break it up into components so we're all on the same page. So we have our r hat vector, or let me write it this way. So we've got r hat over here. So r hat is going to be equal, since it's a unit vector, the magnitude is 1. So the x component is cosine 26.5 degrees. And then our y component is in the negative y direction, right, because it's down. So then we have minus sine of 26.5 degrees. And that's our r hat vector. So then we just take this and plug that in right there. So our full electric field in component form would be 1 over 4 pi epsilon naught, 3 over 20. And then we have cosine, oops, I forgot my x hat. This should be in the x direction. This is in the y direction, sorry. So it's 26.5 degrees x hat minus sine of 26.5 y hat. And that's our electric field in component form. And then obviously you could plug this into your calculator, get a numerical value for that. You could multiply it all out if you want. That doesn't matter too much. The important thing is to get the angle right and get the negative sign here. Okay, so this is our electric field down here. Now let's go on. Okay, so let's talk about vector fields now. Okay, so a vector field is kind of exactly what it sounds like. It's just a function that at each point in space has both a magnitude and direction. So it assigns a vector to each point in the space, and a single vector. There are never two vectors or multiple vectors per point. It's always just one vector in one direction. So there are lots of vector fields. If you've done vector calculus, you've seen this already. The electric field is a vector field, as I mentioned. The magnetic field is a vector field. Gravity is technically a vector field as well. That's you could see that in the acceleration due to gravity, right? At each point in space, there's an acceleration vector. There's a direction that gravity is pointing, and that's because gravity is a vector field. And gravity never points like in two directions at once. It just points in one direction, right? You just fall down. You don't fall like in two directions at once. So velocity is not a vector field because it's just a single vector. There's not velocity at every point in space. It's just an object has a velocity vector. So velocity is not a vector field. So these are just two examples of vector fields here. We typically denote bigger magnitude for the vector as like a different color. Otherwise the vectors just get too big and it's hard to look at. So the red here just means the vectors are bigger. So this is just x hat plus 0 in the y hat direction. That's why all of the vectors are pointing in the x hat direction. And there's no component in the y hat direction. And this is just the first quadrant here. And then this vector field, sorry, I know the colors are a little bit hard to see. I think, I forget exactly which one this is. I think this is sine x hat plus cosine y hat. Something like that. I'm not entirely sure I got my x's and y's in the right place, but it's some combination of sines and cosines. Okay, so to look back at our previous electric field of a point charge, this is what the vector field of an electric positive point charge looks like. So these vectors here, remember the red is bigger magnitude. So these vectors here, the red ones, are much bigger than out here. And this goes in all three dimensions of space. So the electric field of a point charge is symmetric no matter how you rotate it, and it goes radially outward. Now another thing to keep in mind, which we'll talk about more as we go on, is this 1 over r squared here, this r squared in the denominator. So that's very important, and that means that our electric field, let's draw that here. So that means that our electric field, if we were to plot it, falls off very rapidly. So let's say this is r, and this is the value of the electric field. Whoops. So that means that as we move away from the origin, the electric field has an asymptote near this axis, and it goes to 0 at infinity. And that's because of this r squared. So very, very close to the point charge, it gets almost infinite. That's a problem we might talk about later. But your electric field is huge right near your point charge, and then it falls off very, very rapidly and goes to 0 the further you get away. Okay, so keep that in mind. This is what your electric field of a point charge looks like. Okay, so now let's talk about ways to visualize the electric field a little bit better. So electric field lines were developed by Faraday, who we'll meet later. It's said he developed these because he never had like a formal education in math, so he like couldn't do the math of electricity, but he was like a genius experimentalist and came up with these field lines as a way for him to understand what he was working with. So electric field lines show where a positive point charge would go if placed in this electric field. So I know it's a little bit confusing because now we've got, it seems like an extra positive charge floating around. So let's say I have a positive charge. It emits an electric field in all directions. So I've got an electric field going outward like that. All the electric field lines tell you is that if I were to place another tiny little positive charge, let's say there, this positive charge would follow this arrow and just kind of keep going out into infinity. It will be pushed away by this other positive charge because like charges repel. So the field lines just show you the direction that a positive charge would go if placed in that electric field. And then the arrows are just reversed for a negative charge, right? If I had a negative charge here, so I have a negative charge, my electric field points towards a negative charge. So that means if I put a tiny little positive charge here, it would be drawn towards this negatively charged electron. It would go in this direction. So the arrows on a negative charge are kind of just reversed. The field line arrows are just reversed because a positive charge would want to go towards a negative charge. So electric field lines always start on a positive charge, right? They're starting on this positive charge and end on a negative charge. These little lines point towards this negative charge and they end here, or at infinity. So let's say we have two charges. So we have a positive and a negative charge near each other. This is actually a dipole, which we'll talk about later. And the field lines for this dipole will be like this. They'll go from the positive charge to the negative charge. And they'll sort of be shaped like this. So they go from the positive charge to the negative charge or out to infinity. So they go out like that and then they come in. So that's what our field lines look like when we have two oppositely charged particles right next to each other. And then the other thing is the density of the field lines is proportional to the strength of the field in that region. So for example, right here next to the point charge, the density of field lines is high, right? Because we have a tiny area right here, and we have 1, 2, 3, 4, 5, 6, 7, 8 field lines in this tiny little area. Now, if I went out further here, this is now encompassing a bigger area, but I still have the same number of field lines in this bigger area. So the density has decreased, which means the field strength has decreased, which is what we would expect because we said before that as you go further and further away from the charge, the electric field decreases in strength. So that's all the field lines are telling you. When they're very far apart, the field strength is low, and when they're very close together, the field strength is higher. And then the other thing to keep in mind about field lines is that be careful distinguishing between a vector field and field lines. Those are two different things, even though they kind of sound similar. All vector fields, you can draw field lines for any vector field. It's just a way of visualizing what the field looks like. So the vectors of a vector field are tangent to the field lines. So remember, the vectors of a vector field and the field lines are two separate things, and the vectors of that field are tangent to the field lines. So if I were to, let's copy this little dipole here. So for my little dipole here, the direction of the electric field is tangent at every point to the field lines. So right here, a tangent is like that. So that's the direction of the electric field at that point. Right here, the tangent is like that. So that's the direction of the electric field. And you can do this, anywhere. So your vectors of your vector field are tangent to the field lines. And now, sort of like a corollary of that, as I mentioned before, is that since a vector field only can have a single vector per location in space, per point in space, that means that your field lines can never cross, right? You can never have field lines that will go like that, because that means that your electric field then is pointing in two different directions at the same point, and that can't happen. So your field lines will never cross. Whether we do electrostatics or electrodynamics, our field lines will never cross. And then a nice thing about the fact that the electric field is a vector field is that it obeys the superposition principle. So remember, for vectors, if you have two forces acting on an object, you can just add them together as vectors and you get the total force. The electric field behaves exactly the same way, which is really very nice because it doesn't have to behave that way. So that's very nice. So if we have, let's say, just some distribution of charges, and we wanted to find the total electric field at some point, like let's say out here, all you would have to do is just say, okay, well, what's the electric field due to this charge? What's the electric field due to this charge at that point? What's the electric field due to this charge at that point? And then just add them up to find the total electric field. So our electric field obeys the superposition principle, and this will hold true no matter how many point charges you have. So if we had like 1,000 point charges here, you would just add up 1,000 individual electric fields at that point, and you would get your total electric field at that location. Okay, so let's do an example with this. So we want to find the total electric field at the origin due to this charge distribution. So we have 3 charges. We have a negative and 2 positives. And let's find the total electric field at the origin. So we'll call, let's see. So let's start over here. We'll call this charge 1. So we have charge 1 here is our first negative charge. So the electric field is going to be of this form. Oops. So we've got 1 over 4 pi epsilon naught. Our charge here is negative q. So let's just plug in negative q. The distance, we're looking at the origin. We want to find the total electric field there. So the distance from this charge to the origin, this charge is located at d comma 0. So this distance is just d. So we'll just plug in d squared. And then the r hat vector here. So r hat goes from our point charge to the location that we are measuring the field. So that is in this direction. And that is the negative x hat direction in this case. So we have negative x hat. And now you'll notice here that we have 2 negative signs, right? We have a negative from the charge and a negative from the direction here. And so these will obviously cancel out and give us an electric field from this negative charge that overall is pointing in the positive x hat direction, right? So when we multiply those 2 negative signs together, they'll cancel out. It'll give us an overall positive. So that makes sense, right? Because we expect over here, we expect the electric field to point inward for this charge, right? We expect the electric field to be going towards a negative charge. So that makes sense. So be very careful of your negative signs. That's also like probably the number 2 thing that people make mistakes in this class, is just kind of losing their negative signs. So always double check that your answer actually makes physical sense when you're doing these problems. Okay, so that's our answer for charge 1. Now charge 2, let's say, is this one. So charge 2, we're going to have, I'll call this E1, E2. We're going to have 1 over 4 pi epsilon naught. The charge here is positive, so we just have plus q. Then the distance, this one's at 0 comma d, so this distance again is just d, so we're going to have d squared. And then the direction here, so from this positive charge to the point we're measuring the electric field, which is the origin, this is in the negative y hat direction, right? Because it points downward. So we have negative y hat here. And that makes sense because now we just have an overall negative sign. So the electric field at the origin, due to just this positive charge here, points away from the positive charge, which is what we would expect. So now let's do charge 3. So I'll do, let me move this. Okay, so charge 3, this last charge here, we have E3 is 1 over 4 pi epsilon naught. And again, the charge is just Q. The distance from here to the origin is again just d squared. So we have d squared. And then our r hat vector from this charge to the origin is pointing in the positive x hat direction. So we just have positive x hat here. And again, that makes sense because overall we don't have any negatives or anything. So the electric field from this charge at the origin points away from our positive charge, which is what we'd expect. So now we just have to find the total. So E total is just going to be E1 plus E2 plus E3. So we'll just have, let's see, I'm going to factor out the 1 over 4 pi epsilon naught. So we'll just get 1 over 4 pi epsilon naught. And then we have negative q over d squared in the negative x hat, so that will overall be a positive. Then minus q over d squared in the y hat, and then plus q over d squared in the positive x hat. So we can add up our x components here. So overall we get 1 over 4 pi epsilon naught, 2q over d squared x hat, minus q over d squared y hat. And that's our total electric field now at this point. Obviously, you can still factor out the q over d squared and put it out here. That's fine. Or just leave it like this is fine too. So that means that overall, at the origin, the total electric field kind of points in that direction. It points in that fourth quadrant there. Okay, so now let's move on to the electric force. So if you just have a single charged particle, there's no force involved. Just like if you have a single mass, if you just have one planet in the whole universe, to talk about like a gravitational force doesn't really make sense. You need that second object, right? So it's the same in the electric force. You need two charges in order to feel a force. So the electric force is just the charge times the electric field. Now be careful here because this Q here is the Q that feels a force. So this force is the force that this charge Q feels. This electric field is some external electric field due to some other charge. So what this equation is saying is that some charge Q feels this force due to this electric field. And this looks very similar to when we talked about the gravitational force. We have mg, right? Where m is some mass, feels a force due to the gravitational field of some other mass, right? So, okay, so there's a little bit of we can start seeing that gravity and electromagnetism are oddly similar, so we'll talk about that later. Okay, so let's do an example just to see how this works. So we have a charge, so let's say we have some number line here. So we have some charge sitting a distance r from the origin. So let's say Q1 is over here, and it's some distance, this is a distance r from the origin. Now we bring in another charge, Q2, and place it at the origin. So this is charge 2. We want to know what force will Q1 feel due to Q2. So that means what force will this charge feel due to the electric field created by this charge. So this charge we know is going to create an electric field that points outward. And since they're both positively charged, you can guess that this charge is going to feel a repulsive force in the positive x direction, pushing it away. So let's just see this. So we have F on charge 1. So we have Q1 there is equal to the electric field due to charge 2. So we have Q1, the electric field due to Q2, is Q2 over R squared. That's the distance between these two, right? The electric field of charge 2 at the location of charge 1. That's a distance R squared away, or distance R away, and then squared. And then the direction of that is in the positive x hat direction, right? The electric field of this charge points in the positive x hat direction over here. So this is positive x hat. So we have Q1, Q2, R squared. Oops, I forgot my 1 over 4 pi. In the positive x hat direction. So here, this is what's known as Coulomb's law. So Coulomb's law is how we, the formula for the force between 2-point charges. So it's very important that you remember it's for point particles only. If you have like different shaped things like a charged cylinder and a charged rod, this formula no longer holds. This is only for point particles. And all it's saying here is we have the 1 over 4 pi epsilon naught. We have our charge 1 and our charge 2. The distance between those two charges, and then r hat is just the unit vector that points from our charge 2 to the charge 1, the charge that is creating the electric field to the charge that is feeling the force. Okay, so let's do an example with that now. So here we have two positively charged particles, and they're fixed on the x-axis. So charge 1 is 1.6 times 10 to the negative 19 Coulomb, so it's like a proton. And charge 2 is 3.2 times 10 to the negative 19 Coulomb, so that's twice our fundamental unit of charge. The particle separation is 0.02 meters. What is the magnitude and direction of the electrostatic force on particle 1 due to particle 2? So the electric force on particle 1 due to the electric field created by particle 2. So we can just write our Coulomb's law for that. So we've got Q1, Q2, forgot my 4 pi again, R squared, R hat. So now let's plug some things in. So we've got 1 over 4 pi epsilon naught. Q1 is 1.6 times 10 to the negative 19 coulombs. Q2 is 3.2 times 10 to the negative 19 coulombs. And the distance between them is 0.02. So we have 0.02 squared. And then the distance from the charge creating the electric field to the charge that is feeling the force, this is in the negative x hat direction, right? From this charge to this charge is in the negative x hat direction. And that makes sense because we expect these particles to repel each other. So the fact that Q1 feels a repulsive force in the negative x hat direction makes sense. So then you can just multiply out these numbers, and let's see, this comes out to 1.15 times 10 to the negative 24 newtons, so that's a very small force, in the negative x hat direction. And now you could obviously put the negative if you want to put it in front here, and then just have x hat, that's totally fine also. Okay, so we have a very small force when we have these small charges over here. Okay, so that's our force on Q1 due to Q2. And now you can also check if you wanted to solve it, instead of using Coulomb's law, you wanted to do it as QE, where this is charge 1, this is the electric field due to charge 2. You would see that you get the exact same answer. You would get this answer. So, all right, let's try a slightly more complicated example. So just like the electric field obeys the superposition principle, so does the electric force. So if we want to find the total force on a particle due to multiple charges, we just add up the individual forces. So now we have the exact same setup as we just had. We have charge 1 and charge 2, but now we add a third charge here at a distance of 3/4 r down the x-axis. And this charge 3 is negative 3.2 times 10 to the negative 19. So now we want to know what is the total electrostatic force on charge 1 due to charges 2 and charge 3. So we're going to have the force total is the force on 1 due to charge 2, and the force on 1 due to charge 3. So we already found this. That's what we just found in the previous example. So now let's find the force on charge 1 due to charge 3. So that's going to be 1 over 4 pi epsilon naught. Our charge 1, charge 3, the distance between them, and then that r hat. So let's plug some things in. Charge 1, we said, is 1.6, right? Yes, 1.6 times 10 to the negative 19 coulombs. Charge 3 is negative 3.2 times 10 to the negative 19 coulombs. And the distance between them is 3/4 of 0.02 meters. And then we square that whole distance. Now be very careful when you're plugging this into your calculator that you do 3/4 of 0.02 and then square that whole thing. Don't accidentally just square the 0.02. That's again a very common mistake I see, especially with calculators. It's very easy to make. Okay, so we're squaring that whole bottom denominator there. And then our r hat. So again, r hat is going to be the vector from this charge to this charge that's feeling the force. That's again in the negative x hat direction. So we have negative x hat. And we can see overall that the force that charge 1 feels due to charge 3 is actually going to be in the positive x hat direction, right? Because we have a negative and a negative, so that will give us an overall positive force in the positive x hat direction. And that makes sense because these are oppositely charged, so it makes sense that Q1 will actually feel an attractive force towards charge 3. So, all right, let's multiply that all out. So this comes out to 2.05 times 10 to the negative 24 newtons in the x hat direction. And then we can just add up our two forces and get the total force. So F12 plus F13 is 1.15 we had, negative 1.15 times 10 to the negative 24 in the x hat, plus 2.05 times 10 to the negative 24 in the x hat, gives us a total of 9 times 10 to the negative 25 in the x hat direction, and that's in newtons. So we just added those up as vectors. And that's our total force now. So overall, charge 1 feels a force in the positive x hat direction. Okay, and then just one little source of confusion sometimes is, even though Newton's third law has Q1 and Q2, remember those, it doesn't really matter which charge you call Q1 and Q2, because the charges are going to feel equal and opposite forces, right? If we have a positive charge here, and a negative charge here, the positive charge is going to exert an attractive force on the negative charge, and the negative charge is going to exert an attractive force on the positive charge. So they're going to be equal and opposite in magnitude. So also, one thing that I recommend is, since it's very easy to make mistakes with your negative signs, especially when you are figuring out like which direction does r hat point in. So always with any of these Coulomb's law problem, always just think beforehand, do I expect my force to be attractive or repulsive? Is that in the positive or x hat direction, positive y hat, negative y hat? Make sure you figure out conceptually which direction your force should be in. That way, at the end of your problem, you can just double check and make sure that your answer makes physical sense, because negative signs are probably, like, again, one of the most common sources of error in this class. So just make sure that your answer always makes physical sense, and that you understand why a force is attractive or repulsive in any particular problem. Okay, so one little tangent that we should just mention is I kind of alluded to before that electricity and or the electromagnetic force and gravity are sort of similar, and that's because they both have a 1 over r squared force law, right? When we did gravity in 7C, you probably saw this formula for the gravitational force. And this sort of looks exactly like Coulomb's law, right? We have a constant, and then Q1 and Q2 r squared. So these look essentially the same, right? They're just different variables. So it's actually very weird that gravity and electromagnetism look sort of exactly the same mathematically in that sense. And the reason that is, and also the reason why this is exactly r squared down here and not r to the 2.00001 or 2.5, like it's very nice of nature to just give us r squared instead of like r to the 6.2. And the reason that is because both gravity and electromagnetism are mediated by massless particles. The photon is massless, as we said, and if the graviton is discovered, it will also be massless. So if you take like quantum field theory in grad school, you'll actually be able to see the proof that says that any force that's mediated by a massless particle is required to have a 1 over r squared law and exactly a 1 over r squared law. So that's the reason that electricity and magnetism look so similar, one of the reasons. All right, so that's all the material for today. Tomorrow we'll finish up chapter 21, and I'll see you guys then.